Magnetism. Magnetism is a force exerted by magnets when they attract or repel each other caused by the motion of electric charges. Opposite poles attract and like poles repel. Magnetism is a non-contact force represented as a field, always drawn north to south. If broken in two, it will form two magnets since magnets are natural dipoles, which means there will always be a north and a south. This is our Earth, geographic north and geographic south. However, magnetic poles are complete opposite. It's the reason why compass points to geographical north, because magnetic poles are opposite, so it attracts. Since moving charged particles create magnetic field, current creates magnetic field. Wait, how do we know the direction of the magnetic field? We can use the right hand rule. This is your right hand. Point your thumb in the direction of current. Curl your fingers, and that's the direction of magnetic field. In this example, there's a wire with current going to the right, so point your thumb in the right. Curl your fingers, and that's the direction of the magnetic field. So for point P, the direction of the magnetic field will be out of the page, and for point Q, the direction of the magnetic field will be into the page. And those are the symbols that usually represent into the page and out of the page. To calculate the strength of magnetic field, we can use this equation. B is strength of magnetic field in Tesla, I is current in amps, R is distance from wire to point in meter, and constant 4 pi times 10 to the negative 7. When moving charged particles goes through magnetic field, it feels magnetic force. To calculate force on a moving charged particle, we can use this equation. F is force in newtons, Q is charge of the particle in coulomb, V is velocity meter per second, and B is magnetic field strength in Tesla. Velocity and magnetic field must be perpendicular to apply force. To calculate force on a current-carrying wire, we use this equation. F is force in newtons, L is length of wire in the magnetic field in meter, and I is current in amps, and B is magnetic field strength in Tesla. Current and magnetic field must be perpendicular to apply force as well. What direction the force is applied? We can use the right-hand rule number 2. Point your thumb in the direction of velocity of moving charged particle or the direction of current in wire. Then, point your pointer finger towards the direction of the magnetic field, and the middle finger will be the direction of force. In this example, the moving charged particle is going to right, so point your thumb to the right, and then point your pointer finger towards into the page since the magnetic field is into the page. And then the middle finger will point upward, so the force is applied upward, so the moving charged particle will curve upward. Faraday's law. First, magnetic field surrounds the current-carrying wire, and second, a changing magnetic field creates a current. Induced current is current created by using a magnetic field. Induced voltage from the induced current. Flux is amount of magnetic field in an area. Flux we can calculate using this equation. B is magnetic field strength in Tesla, A is area field in meter square, and flux in Webers. And you can think of area field as area of coil in the field, and magnetic field and area field must be parallel. EMF, electromagnetic force, is induced voltage in volts, and we can calculate that using this equation. N is number of loops times change in flux divided by change in time. When a moving charged particle enters the magnetic field, what's the direction of the induced current? We can use the right-hand rule number 3 to figure that out. Point your thumb in the direction of magnetic field and curl your fingers. That's the direction of the induced current. In this scenario, with the direction of the magnetic field going into the page, the current must be going in clockwise, right? However, since the coil is entering the magnetic field, the current is actually going in the opposite direction because the magnetic field wants to stay like before. In this scenario, where the coil is exiting the magnetic field, the current is going in clockwise. Since coil is leaving the magnetic field, the direction stays the same with right-hand rule number 3, so current is going in clockwise. So what about if the coil is in the middle of the magnetic field, not entering or not exiting? Well, there's no change in magnetic field, or in other words, no change in flux, so there's no current. Thanks for watching, and I hope you learned a lot about magnetism. See you soon!